So remember, the weighted average cost of capital is just a way to sort of combine the interest rate that we're paying on debt and the return on equity that we might owe to shareholders into a single numerical weight, with each one of those individual rates weighted by the portion of the capital cost that's financed with each mechanism. So D here equals the portion of the capital cost financed with debt. E equals the portion of the capital cost financed with equity. KD is equal to the interest rate on debt, and KE is equal to the return on equity for shareholders. And we can plug in some numbers here. We said that 75% of the capital cost is going to be financed through debt, so that that's going to be $750 million. 25% of the capital cost is going to be financed through equity. That's going to be $250 million. Return to interest rate on debt is 5%, and return on equity for shareholders is 11%. So we can plug those numbers in here, and what we end up with is a weighted average cost of capital of 6.5%. So we're going to assume that 6.5% is our discount rate for this discounted cash flow and net present value analysis. So when we go back to our discounted cash flow analysis and we're looking at discounting profits in every single year, we're going to use this generic formula, which is that the present value of profits in any given year, in other words, the discounted profits, equals the profits in any given year divided by 1 plus 0.065 to some sort of exponent, where that exponent equals the year that we're talking about. And then we would sum those all up to get net present value. So how do we estimate annual revenues? So we're talking about a coal plant, right? So coal plants make money by doing what? By selling electricity. So that's partially what's going to be involved here. Revenues are a product of the amount of electricity that's sold, as well as the price of electricity that they're gonna sell at. So what determines how much electricity the plant should optimally sell? So we're not going to assume that we know at the very beginning of this analysis how much electricity the plant's going to sell. We need to sort of figure that out as a product of something else. And what we talked about in the lecture on firm decision making is that the optimal amount of a product or a good that a firm should produce depends on price. So we actually need to know what the marginal cost of electricity is from this coal plant, but also the market price of electricity. So let's start by talking about market prices. We're going to assume that this coal plant is operating in a competitive market where the interactions of supply and demand are what determine market prices. And so we need to sort of think back about what information we have that could help us determine what market prices are. We talked earlier in the lecture about the larger market environment, and that this market, this competitive market for electricity, has a system supply curve. Now remember, this system supply curve does not refer to the individual supply of electricity from this particular coal plant that we're talking about. This is the larger system or market's ability to provide electricity and the price at which they would be willing to sell electricity for different amounts or quantities of electricity supplied. So this is our system supply curve. So that's half of what we need to determine what the equilibrium or market price would be. We also need electricity demand, and we talked earlier in the lecture about how we would think about estimating electricity demand. So the way we thought about it is that there are 365 days in the year, and we're going to just assume, just to make things really simple, that half of those days are either fall or winter days, and half of those days are spring or summer days. And that those two different types of days have different electricity demands that vary throughout the day. And that's what these two line graphs show. On the blue side, it shows how electricity demand changes throughout a fall or winter day. And the green line graph on the right shows how electricity demand in spring and summer days would change throughout the day. So let's zero in on one of these categories, the fall and winter days. And so now what I'm showing you is that same line graph that plots quantity of electricity demanded for each hour of the day. And what I'm showing you in the table is that same information. Where we have the first column is the hour of the day from 0, midnight, to 2300 or 11 p.m., and also the quantity of electricity demanded in megawatt hours. So that information in the first two columns is exactly what's plotted on the figure on the left. And now what we want to do is estimate the price of electricity, the market clearing price of electricity at each hour of the day, where at each hour of the day we have a different demand for electricity that we can use to interact with our system supply curve to estimate wholesale prices for electricity. So let's see how that would work. We have the system supply curve that's shown in blue here, and what we can do is look at how the demand for electricity interacts with that system supply curve. So in every hour of this hypothetical fall or winter day, we have 24 different hours to look at. We have some sort of quantity of electricity demanded, and whatever that quantity of electricity demanded is corresponds to the placement of this vertical yellow line on the top right graph, right? So we see some sort of demand for electricity at midnight. And we see that quantity of electricity demanded is 15,000 megawatts. So 15,000 megawatts are demanded, megawatt hours are demanded in the very first hour of the day. And so that vertical yellow line is placed right at 15,000 on the value of 15,000 on the x-axis. And so we draw this straight up and down line because demand for electricity in wholesale markets is perfectly inelastic, which means it's straight up and down. And so what we see is that system supply curve in blue intersects with our demand curve, our perfectly inelastic demand curve in yellow. We can estimate the price of electricity as the value on the y-axis that's associated with that intersection. So we can draw this yellow line from our intersection over to the y-axis. Now, it just so happens that if we look at our system supply curve, there is a price that's a value of the y-axis that is specifically associated with a demand of 15,000, and that price is $22 per megawatt hour. What that means is that the yellow dotted line indicates a price of $22 per megawatt hour. In other words, the yellow line, the intersection between our yellow demand curve and our blue system supply curve, occurs exactly at the place on the y-axis that's associated with $22 per megawatt hour. So we can fill in the rest of these prices the exact same way. We can use that table of our system supply curve as well as corresponding values of electricity demand throughout the day to calculate the market clearing price of electricity, where that market clearing price is the value on the y-axis that's associated with the intersection of our system supply and our demand curves. And so we can do this for not only the fall and winter days, but also for the spring and summer days. So we have prices. We know that we're still working on trying to figure out what revenues are. We're doing a net present value estimate of this power plant. We're trying to project discounted cash flows out into the future. A part of that is what revenues are. So far what we've tackled are the prices for electricity at which this plant will be able to sell electricity. However, we don't know yet how much electricity will be sold from this power plant. The question posed here is, we know what the installed capacity or the size of the power plant is. That's 700 megawatts, which means that at any given point, it could be producing 700 megawatts of electricity. However, the question is, will the plant just operate like that? Will it turn on, ramp up to 100% capacity, and stay on at that level, producing at that level, for every hour of the entire year? And the answer is no, right? Because we know that the amount of goods that a power plant should produce, in theory, if we're going to adhere to this microeconomic principle of maximizing profits, is that whenever their marginal cost is less than the product price, they should produce one thing. And whenever the marginal cost is greater than the price, they should produce another amount. So let's try to fill in the blanks here. If we recall from our lecture on firm production decisions, you'll remember that whenever the price is greater than the marginal cost, that means they should produce as much as possible to maximize profits. And whenever the price is less than the marginal cost, that means they should produce nothing at all because they would be producing and selling something for a price that is less than it actually costs them to manufacture it. So we can fill in these blanks here. Whenever we see that the marginal cost is less than the price, we're going to assume that the plant is producing at maximum capacity. And whenever the plant's marginal cost is greater than the price, we're going to assume that the plant produces nothing. So we do have some information to fill in here. At the very beginning of this exercise, I gave you what the marginal cost of electricity production would be for this power plant. We didn't derive it from specific cost information. We just assume that we're going to assume here that it's $20 per megawatt hour. So we can actually fill in that information here in these rules of thumb. So now we're going to go back and look at the price data that we have. And every time that we see the price is less than $20 per megawatt hour, we're going to assume that the plant produces nothing. And every time that we see that the price is greater than $20 per megawatt hour, we're going to assume that the plant is going to produce at maximum capacity, or 700 megawatts. So let's go back and see how often these conditions are met. We have calculated prices for every hour of the day in these two different categories of days: fall and winter days and spring and summer days. And we calculated prices using the intersection of a perfectly inelastic demand curve, which just shifts left to right depending on what quantity demand it is, along with our system supply curve, or the market's ability to produce electricity at different prices. Well, anytime we see that the price is greater than $20, we're going to assume that the plant is on. And for every hour, you can see where that is the case here. We've highlighted it yellow. And then for every hour in which the price is less than $20, we're going to assume that the plant's going to be off. And in every case here, we've left those lines unhighlighted. So this gives you a sense for during which periods of the day and how often during these two types of days, fall and winter days and spring and summer days, this plant would be active. And what it suggests is that in the fall and the winter, this plant is probably going to be producing electricity in the morning, maybe through lunchtime, and then it's going to turn off during the middle part of the day, and then it's going to turn back on in the late afternoon and evening. And then in spring and summer days, the power plant's going to be off during the early part of the day when electricity demand is lower. And then as electricity demand and price increase, this power plant's going to turn on in the morning and stay on for the rest of the day. So we want to take that one step further. We want to actually figure out how much money the plant would be making. So let's focus again here just on fall and winter days. And here we've added a couple different new columns. We still have those first three columns of the hour of the day, the quantity of electricity demanded, and the price of electricity. And those prices vary throughout the day with demand, because as demand increases, the price tends to go up. For every price that we see here that's greater than $20, we're going to assume that the plant is on. Those rows are highlighted in yellow. And now we're also adding a binary condition here. So anytime it's on, or the price is greater than $20, we're going to put a 1 right next to the price. And anytime that the power plant is off, or the price is associated with a value that is less than $20, we're going to put a 0. And so those ones and zeros become useful when we want to actually calculate revenues, because then we can create a column that's on the other side of the on question mark that tells us how much electricity is produced. And so all we have to do there is say, put a little equation in that column where for every row in the produced megawatt hours, we're going to have that value equal to 700 megawatts times whatever the value is in the on column. So if the value of on is 1, indicating that the plant's on because the price is greater than $20, it will produce 700. And any time that the plant is off because the price is less than $20, we're going to get a value of 0 in terms of megawatt hours produced. And then we have one more column to think about all the way to the right, and that is revenues. So the revenues are just equal to the amount of electricity that's produced times the price. So the price changes in every hour. And in some hours, the plant is producing some, and in other hours, it's not producing any. So you can see the revenues that are produced are all positive and non-zero in every hour that's yellow, where the plant's on. And the hours where the plant's off, it earns no money, so its revenues are zero. But even within the group of hours where the power plant is producing electricity in yellow, the revenues are different. And that's because the price is going up and down. So for example, in fall and winter days, when the power plant is producing at about 7 or 8 o'clock in the morning, its revenues are higher. And that's because the price is pretty high. It's $30 per megawatt hour. And then if we look towards the end of the day, when the power plant's producing at about 10 o'clock or 8 o'clock, and then if we look at the end of the day, when the power plant is producing at around 8 o'clock or 9 o'clock, it's earning even more money, producing the same amount of electricity because the price increases still further to about $32 or $35 per megawatt hour. And that's associated with the highest demand of the day, which would be people coming home from work and cooking dinner and turning their heat on. So we can also add the revenues up for every single hour of the day. And the total is shown here at the bottom. It shows that on fall and winter days, this coal plant we're going to estimate earns about $336,700. And we can do the exact same thing with the spring and summer days. We have a couple extra columns here, one for the on, which just is a binary 1-0 condition, describing whether the power plant is on or off. We're assuming that if it's on, it's going to be producing 700 megawatt hours, and if it's off, it's going to be producing nothing. And so those ones and zeros allow us to create a formula in the produced megawatt hours column, where that formula is equal to 700 times whatever the value is in the on column. And so if we say 700 times 0, we just get 0 produced megawatt hours. And if we say 700 times 700 megawatts times 1, we get 700 megawatts. And so what's clear here is that this power plant in the summer and spring is going to be active in the morning, starting at about 7 o'clock all the way through the end of the day. And in the early morning hours before that, it's not producing any electricity. So its revenues are going to be zero, because revenues here, again, are the amount of electricity that's produced times the price. And you can also look within the number of hours, the set of hours where the power plant is online producing electricity. Again, the revenues are different. Even though it's producing the same amount of electricity in each one of these hours, the prices of electricity are much different, especially if you sort of look towards the highest demand periods of the day, which would be, if we're talking about spring and summer, would typically be the hottest part of the day when everybody's using their air conditioning. So maybe 3, 4, 5 p.m. You can see that actually at 4 p.m., demand increases so much that the price of electricity goes up to $100 per megawatt hour. And so that's when this power plant is really starting to make money. It earns $84,000 just in 1 hour. And so again, we can figure out total revenues for a day, a spring or summer day, by adding up hourly revenues for each one of these 1 through 24 or 0 through 23 hours, giving us a total of $487,900. So now we finally have an estimate of revenues for this power plant, because we are able to calculate market prices for electricity in this wholesale competitive market. And using those prices, we were able to identify what the optimal production level would be for in each hour of every day for this power plant. And this gives us an ability to calculate revenues for each type of day. And we have 2 types of days, remember, fall and winter days and spring and summer days. And so all we have to do is multiply the number of fall and winter days that we have times the daily revenues for that particular type of day. So 182 times 336,700 plus revenues on all our spring and summer days, and that would be 487,900 times the number of spring and summer days, or 183. If we add this all up, what we get is total annual revenues of $150,565,100. So we can go back to our discounted cash flow analysis and start to fill some numbers in. Remember, in year 0, we typically would not consider any revenues for this power plant. We're going to assume that it takes a full calendar year to build the power plant. In reality, it takes often many more years than this to build a power plant, but we're just going to, for the sake of simplicity, assume that it takes 1 year. Plant construction takes 1 year, but over that time period, they won't be selling electricity. In every other year, however, year 1 through 25, over the lifetime of the power plant, we're going to assume that it's going to be selling the same amount of electricity every single year, and that revenues are also going to be the same every single year, equal to $150,565,100.